So again, we see the optimum spot here where I'm only showing the shin and I'm showing the foot and the universal joint down there. And you can see down the bottom where these balls are for the Heim joints. And the trick to solving this problem is we need to think about a couple of coordinate systems here. So right here at the ankle, this is the world coordinate system. This does not move. And the shin doesn't move either, except up here is connected to the knee. So obviously it's rotating there. But for all intents and purposes, this shin is rigid to the world frame of reference, which is defined by here. And up here, we have the spherical joint in the SPU. So that's the sphere they're talking about that I've labeled as P1. And that's always a fixed offset from here to there. And then we also have this point here, P2, which is also, it's going to be a moving frame. So we have to sort of figure out where it is with respect to the world as we go along. Now, what I want to do is I want to calculate these three vectors. So this blue vector, which is a distance basically from here up there, but it's basically a vector because it has a position in space with respect to the world frame. And then I want to calculate this purple one, but this purple one changes in length. That basically is what is going to tell me how much I need to actuate this whole thing, dependent upon how much the foot moves around. And there's going to be this little orange frame down here that I'm going to need to calculate. And so the first thing is like this blue frame here, that just comes out of the engineering drawings. You measure it once and that's it. You know, it's just it's given, just some numbers that are there. So you don't have to worry about that. Now, the next thing I'm going to do is I'm going to kind of zoom in here a little bit closer and start labeling this a little bit better. So I do that so everyone doesn't get lost. So what's happening down here at the ankle is you have the very first rotation of the universal joint is this green. That's the foot pitch. And then after that pitches, it results in this whole structure moving, which means there's now an offset that goes here in the blue down to the center here. And then you have this rotation in the red, which is the roll. Okay. And then from here to there, this white vector, that vector is fixed. That's also given. So the distance from here to there in that particular part space is always fixed, it's given. What we have to calculate is this dashed one. That's the thing that's always changing. And that's going to be the position of this point in the world frame, which is the same world frame that the shin has for P1. So they're all in the same frame of reference. So what happens is that when you begin to, what you want to do is basically say that this orange vector is basically equal to this order of operations. The green rotation plus a translation in the local Z of the new frame, then that rotation plus that. So you add all these things together and you will get that. Okay, that's the order of operations. Basically, it means this is what you do, is that you calculate the rotation, you create a rotation matrix about Y of pitch, then you translate in the local Z by whatever that Z offset is, then you rotate about X about this roll, and then you concatenate that with this W vector, and that gives you the P vector. That's the order of operations that you go through. So what ends up happening, of course, is that if you pitch this thing around, you kind of see, okay, we rotate it this way. That blue vector is now not in the world Z, but it's in the local Z. So it's still like a local translation down to there. You do all this stuff, and now that's the new location for P. Now that I know where P actually is, so pretty much what that means is like, take these two numbers. This is a fixed number, that's fixed. Plug that into this equation. You now know where P2 is. And as a result of that, all you have to do is figure out what this purple vector is. And if you kind of look at that, basically the purple vector is the orange vector, which we just calculated, P2, minus the blue vector, which is a constant that's given. So all you have to do is like, oh, that's what the equation looks like, which basically says, oh, if we call that thing L is just P2 minus P1. It's as simple as that. And that means if you take the magnitude of a vector, and remember the magnitude of the vector is just the Cartesian distance. It's the sum, it's a square root of the sum of the squares of each component. So x squared plus y squared plus z squared, take the square root of that, and that's the distance. And that tells you how much you need to offset it. That's it. So that's how you solve the forward kinematic problem. Now, as we've seen, there is a problem of like, well, what's the angle that goes in there? And that's a little bit more because it's a 3D reasoning problem. It's a little bit in there. But I think once everyone gets this far, once you know P1 and P2, you have all the information you need to solve the rest of the problem.